Okay, now if we want to know the Porewater distributions and also the uplift force on upstream and downstream faces of the sheet pile. So we have the sheet piles. We have the cutoff of sheet piles below the concrete dam. So we also want to know the Porewater distributions and also what is the value of the uplift force on the upstream and the downstreams of the sheet pile. Okay, so now we focus on the sheet pile. Okay, we focus on the sheet pile. So we start with the front sheet pile, the front face. This is the front face and this is the back of the sheet pile. Alright, so actually the step is exactly same with the previous method of Porewater pressure distribution. So what we need to do is we divide the length of the sheet pile into an even numbers of intervals. So since the length is 7, so we need that even number, because later we will use the Simpson's rule to determine the uplift force. So we use 6. So 7 meter divided by 6. So each interval or each point will have the distance 1.17. Okay, so I label from point A here. Okay, from point A here, K, L, M, N, O, and P at the end of the sheet pile. So we tabulate the calculation of Porewater pressure for each interval in the table. Okay, so this is for the front face of the sheet pile. Okay, so this is the front face. Okay, so from point A, so which is the x0, we start from that point, x equal to 0, and you can see here the nd equal to 1. Okay, so for the sheet pile, yes, so for the sheet pile, so I will use that the flow line on the left side, that it start from equipotential line number 1. And because all the points will at the face will refer to the flow net on the left side. Okay, so if you can see here at point A, so the ND is equal to 1. Okay, then at the point K, okay, at the point K, if you can see here, so the point K, the ND is located between ND1 and ND2. Okay, roughly we can say that point K is located in the middle, in between ND1 and ND2. So we can estimate that the K ND is equal to 1.5. And also, for example, at point N, so it been between 3 and 4, and roughly we can estimate that point N is around 3.2 maybe. Okay, the ND is 3.2. Okay, alright, so here the same table as previous. So we have the head loss, so delta H, again delta H the same, delta H 0.611, so we just time with the ND. Okay, so we will have this delta H. So again the HT, we have the upstream, okay, 25 again, so minus with this head loss, so this is the HT at point A. So the HE, the elevation, okay, location of point A from datum. Okay, so this is the point A, so the datum at the bottom layer, so we have 13 minus with 1.5, so we have at the point A is 11.5. And then for example at point K, alright, so how we get the HE, elevation, is actually 13, okay, minus 1.5 plus the distance 1.17. So we will have the locations of point K from datum is 10.33. Alright, okay. Okay, so we know that each gap of it 1.17. Okay, so we already have 1.5 here. So the distance between each interval is 1.17. Alright, so the total of 1.5 and 1.17 will be subtract from the total length here, which is 13. So from the datum, the point K is located is 13 minus 1.5 minus 1.17. Alright, so you will have 10.33. So exactly same also. So we have the HP, which is H total minus with the HE. So you will have the HP, and to get the pore water pressure times with the unit weight of water. So you will have the U naught here. Okay, the first value of U. Alright, so complete all the calculation. Okay, you will have the all pore water pressure till 6. Alright, and then plot the distribution of pore water pressure on the graph. So okay, for this case, the y-axis is the depth or the length of the sheet pile, because the location of the sheet pile is vertically like this. Compare with the dam previously, we make the x as a x-axis, but for this sheet pile, we follow the directions of the sheet pile, which is in vertical like this. So that's why the y-axis is the distance or the depth of the sheet pile. Okay, and the x-axis is the pore water pressure. So this is the distributions of the pore water pressure on the front face of the sheet pile. Okay.